Yeah, today we're going to talk about decision trees, what they're about, and interpretable models, and how you can interpret decision trees. There are some things that we are going to be seeing during the course of this workshop, but at the end of it, you understand what decision trees are. We also go through two criterion that decision tree uses. So I mean, when you see DT, it's just a short form of decision trees. We'll also look at what interpretable models mean and how we can interpret decision tree models. We'll also look at boosting algorithms, what a boosting algorithm is, and how they are related to decision trees. And then we will just take a sneak peek into sklearn. So for the sneak peek, I have tried to just minimize it to just going over the documentation of sklearn. But in the references, I've also put like blogs or articles because I just felt it didn't make sense to repeat what some people have done. So if we have more time, we can just look at one of those references and just look at the article together and the code and just go through it and what they have done. So before we like dive into the meat and potatoes of what this workshop is about, I just wanted to know who have seen the Titanic movie, maybe by a show of hand or reaction. Can I just see maybe a reaction or comment in the chat section if you have seen the Titanic movie? Okay, Sarah, thank you. I see that. And anyone else? I hope participants can unmute themselves. Okay, Teju has. Anyone else? I need more volunteers, please. Don't worry, I'm not going to put anybody on the spot. So, so the interesting thing is that I have not seen the Titanic movie, to be honest. I haven't. So, I don't know if Sarah can unmute and just have 1 minute to summarize what the movie is about. Just a summary. I've not seen it, but I've read articles about it. They were traveling, the ship capsized, people died, some people survived, and then there's Romeo and Juliet that are in love, So I am Sarah, if you can unmute, let me see if I can ask you to unmute. I think I can't. I'm not sure. Just give us a summary of the Titanic movie.
I'm very shy, but yeah, so it was basically about a ship where there were many classes, as in rich people, poor people. So a boy from the poor side fell in love with a girl from the rich side. Then the boats did not have a good structure in the first place, so it um crashed when I think it hit the iceberg. I can't remember because I think I watched it in primary school, but yeah.
Wow.
And then the boy basically put her on one of the good lifeboats and then died. That's what I remember.
Okay, thank you. I think that's it. That I think I've not seen the movie to be honest, but I know that it's about people, traveling on a ship, and the boy froze to death. Oh, that's sad. Anyway, so if you have not seen Titanic, at least you've caught up with what we've said, and I would be explaining decision trees. Or let me say, the beginning of this course will cover like I'll be picking some things from the Titanic dataset, which we'll see in the next slide. So that's why I asked if, and it looks like maybe, I don't know, maybe people just didn't want to put their hands up, or, I'll just use the statistics and pretend like only 2 people have seen it, since I only saw 2 people indicate that they've seen the movie. But let's take a look at what the Titanic dataset looks like. So the left side of my screen just shows us the data set in tabular form, and the right side is just the information about each of the columns. And oops, and we have like the passenger ID, which is just an ID, and they survived is if they survived or not, and 0 of course is they didn't survive, and 1 is they survived. The passenger class is basically, when you're in the plane, like first class, second class, third class, that kind of how rich you can afford, how rich you are, and how you can afford, some spots on the cruise ship. And the name, the gender, the age, how many siblings that they have. The patch is just a number of parents or children that were aboard with them, the ticket number, the how much they paid, the cabin number they have, and where they boarded. So at the points at which they boarded the ship. So these are basically the columns. So I believe, you've been doing some classes up until now. So some things are no longer, I believe some things will no longer be foreign to you. You already know like what a data, I believe you know what a data set is. So given this, we'll just move on to decision tree. So what I've just done is, explain, what the Titanic data set looks like. So what are decision trees? They are basically, I'm going to start from, what a typical tree so that you understand, why we call them decision trees. So when you have a tree, let's say you want to sort of chop down the tree based on some criteria. So for example, I mean, this can feel silly, like in terms of like the real agriculture, you wouldn't want to chop down a tree based on, oh, this branch has five leaves or six leaves. But let's say you want to chop down the tree and you are using some certain criteria to do that until you get to the end of like chopping down the tree. So for example, you have a palm tree and you want to chop it down by the tree that are facing the north side or the west side or east side, or or let's say the branches that have certain number of leaves, or the branches that the leaves has withered, right? So you can think of decision trees like that, and you can think of these data sets that are described as, the data, what forms your trees, the branches, the leaves, the fruits, and those characteristics of a tree. Those are, you can just see those as your data sets, and then you are like going through that data set and maybe doing some certain actions based on certain criteria that the features of your tree have. So given that, we can define, decision trees that as a tree that recursively splits your data set until we are left with pure leaf nodes. And we will see, we will go deeper into what are pure leaf nodes, but basically they are the data with only one type of class. But we'll get there. If this is not clear, we'll still talk about, what the leaf nodes are. And decision trees can be used for your classification or regression tasks. So it's not, we have the decision tree classifier and we have decision tree regressor. And I'm going to, I don't want to, I know you've been doing classes in the past, but I'll just pretend that this is a refresher. So classification is when, you are dealing with categorical values. Like our Titanic data set is classification. It could be a classification task if we are trying to predict, let's say, the people that survived, because it's a binary, in that case, it's a binary classification. But let's say we are trying to predict something like the fare, like how much they paid, given the other features. In this case, is a regressor because it's a continuous variable. It's not, we can't categorize, the amounts that they paid. Another typical example of, a regression task is if you are predicting like the price of a house, for instance. So that's not a categorical value, is a continuous variable. And one thing that I wanted to bear in mind is that decision trees, it's not a mathematical model. If you have done, like, I know you've done, you took a class maybe last week or 2 weeks ago on naive Bayes. So that's a mathematical model. It's based on like conditional probabilities and, some of those like different, probabilities theorem anyway. So that's naive Bayes is an example of a mathematical model. Another example is like your normal linear regressor, for instance, or linear regression, as some people may call it. That's a mathematical model. But for decision tree, it is not a mathematical model, and we will see the reason why as we go further in this course. So I've now what we see here is a decision tree classifier using the Titanic data, and you see that the reason why we say it's not a mathematical data, it will become clearer because you see that in this case, we just have a bunch of, we are not, when it comes to mathematical model, like a linear regression, for instance, you are trying to establish a mathematical formula that relates your input features to the output. So in the Titanic dataset, the input features are like the number of siblings, their age, their gender, and our output, for instance, is we are predicting if they survived or not. So you are trying to, when you're using like SVM, like that is, what's the meaning of SVM again? I literally forgot. If someone remembers, it looks like a control flow. Yes, something like that. We'll get to the bottom of it. So in naive Bayes, there's a mathematics to trying to establish the relationship between, thank you so much, Dalam, support vector machine. So you're trying to, fit a line using some sort of formula, to navigate your data such that you can classify where they belong to, or like your linear algebra where you have like you use the linear regression where you use a linear algebra formula, for instance. So you're establishing a formula, a math formula basically that relates your input to your output. But for decision trees, like somebody said, it's like a control flow where we are just using some, if else sort of to navigate our database or our data points. And using that, we would then use that tree, the tree that is the part that is the best in the tree that we have built. We will use that to now, go through an unseen data where we don't know what the output is. So looking at this, for example, this is random, but we have selected, this feature as our very first feature. We are checking, okay, is the gender male or we go through each row. So this is like going through each row of your data and trying to draw trees such that you are able to build an optimal path in your tree that can finally help you to discern or to predict for a particular row where you don't know what the output will be. So looking at this now, we have, is the gender male, and when it is yes, when it is no, it means they survived. So this is random. This is not like this is not the optimal path for this particular, for the Titanic data set. This is just an example. So please bear that in mind. So this means if let's say this is my optimal, let's just pretend that this is my optimal branch, like the part that, we know that is the best in all the branches that we have built for that tree. We want to check, so when we have a new row, for instance, where we don't know if the person survived or not, right? So we come to this tree, and the first thing we want to check for that particular row is, okay, what's the gender of this person? If the person is male, we know that, okay, we start going through some other, conditions, branches, basically. But once the person is female, if this is the optimal part, so please bear that in mind, if this is the optimal part, right? If the person is female, it means that they always survive. So every time I have a new row, like somebody, let's say somebody comes to me and say, this is the data of someone who was on the Titanic ship, but I don't know if they survived or not. I just come to my optimal part. Like that's what the algorithm does basically. It comes to the optimal part and then it passes my data right through these branches and it checks. So the first thing to check is the gender male or female. So as long as the person is female, it means they survive. So this is my optimal part. So they survive. So, but let's say this particular row, the person is male, so it then goes to that optimal pattern. And so, oh, the person is actually male. So yes, they are male. So the next condition I have to check is their age. So what's the age of this person? Are they great? Is the age greater than 10? If the answer is yes, oh, that means they died. So That's my prediction. The prediction is that they died, they didn't survive. But I mean, if the age is lesser than, no, greater than 10, sorry. If it's lesser than 10, there's another condition that I'm checking. Okay, how many siblings did they have? They had, did they have more than two? If they had more than two, it means that they died, they didn't survive. But if it's less than two or equal, in this case, then that means that they survived. So this is how we build decision trees. And you may wonder, like, that's why I have this question. So do you think this is just a thought I want you to have at the back of your mind? We would know, if it's just if else, like somebody said, control flow. Control flow is basically conditional statement that gets us to the right place. So we would know at the end of this class if it is. I'll ask again if it's if you still think it's an if, it's a bunch of if else, because why are we calling it a machine learning model if this is just if else? We will get to know, why. And at the end of the day, what we want to do is to basically build a path, which we can also call a model, that can optimally learn the features to optimally split the data. So when we say split the data, it is this, splitting of the data by the features and navigating through it, such that at the end of the day, when we have a model that represents an optimal path, every time we go to that model with our new row that contains a new data point, we should be sure that that path is always going to get us to the right answer. That is, if they survived or not. So given that, we will now talk about the anatomy of a decision tree. So here we've seen, the decision tree from the lens of the Titanic data set, like a sample of what it looks like from the lens of the Titanic data. Now, we'll talk about the anatomy. So, the anatomy of a decision tree is very intuitive, like very straightforward. The very first node that starts, a particular path is the root node. We call it the root node. It's the starting point for making decisions in the structure of the tree. So when we look at this, can someone tell me? I mean, this is simple. I know I'm just asking like ABC, but this is just for me to be sure that everyone is following. So who can tell me, what is the root node in this case? Awesome. Okay, I don't even ask you. You have brilliant students. Clap for yourself. So yeah, that's the root node, because that is the feature that we have started with. So the root node is the very first node that starts our tree. And then we have what we call the intermediate node, or also known as the decision. Oh, thank you, Dolam. Also known as the decision node. And I mean, some call it intermediate nodes or internal nodes or decision node. Anyone, is fine, but just know that in case, people use different nomenclature. So if you come across maybe internal node elsewhere, just know that it means decision node or intermediate nodes. And they are the ones that lie between, how do I put it? They have an arrow pointing in and out of them. So as you would see here, so that's why we call it intermediate, because they are like in the middle. So something is pointing into them, something is like a branch, rather. Don't let me say something. It's a branch actually. A branch is pointing into them, a branch is pointing out of them. Those are called the decision node. So if we go back here, just because of time, we know that the age greater than 10 is an intermediate, is a decision node there, and number of siblings is a decision node there. So moving forward, so decision nodes are in the middle. They are usually between the root node and the leaf node. And lastly, we have the leaf node. And the leaf node is basically, the end point of the tree branches. So for every branch, the very last node of the branch is the leaf node. So in the previous slide of the Titanic dataset, where you have like the survived, died, those are the leaf nodes, because they are basically at the very end. That's where we are going to, because we want to basically know through all of this navigation, we want to know at the end of the day, this particular data point, what happened to this particular, passenger, did they die or not? So those are the leaf nodes. So let's move forward. So now we are going to build decision. I know maybe some of you are like I said, it's not a mathematical model, so we'll still get there. So there's a place we'll get to the math part of decision trees, but just follow me. This may be looking like basic or something, but honestly, if you understand this, that is decision tree. It's not harder than that. It's not supposed to be hard. So we are going to do like a primary school sort of exercise now. And in this scenario, I have started building my tree and the grad of Ivy. So let me explain the data set. Pardon me. Let me explain the data set. So this is like a data set of applicants for a job. And let's say we want to build a decision tree that can let us know right on time if a particular participant or applicant, not participants now, if a particular applicant is suitable for an interview. So that's basically what we want to try to know with this, with this data set. So the requirement that they have, or let's say the qualification that they have, or let's say the features in this case, is that if they have an MSc, if they are a graduate of an Ivy League school, and then their years of experience, of working. So maybe they have like some gap between their bachelor's and their master's, and they've had some experience. And we've had this data set. So let's say some HR or some people we recruit have been able to sort of, know how they have like an historic data of the people that have been passed for interview. So, but they don't want to manually probably do that. Maybe they use a manual check for that, but they don't want to do that again. And we want to use a decision tree to just pass a particular participant and know if they are suitable or not. So these are the data set, and we have how many rows? We have 7 rows, so 7 data points basically, and then we have 4 columns, where 3 columns are features, and the suitability is what we are trying to get. So we pretend like we don't know this, but this is our data set anyway. So what I want you to do for me now is that you walk through this grad of Ivy. So maybe I'll just explain the first one, and then the class will do the no as an exercise. So my very first, the root node that I have here is if they're a grad of Ivy. So if they are a grad of Ivy, yes, I'm jumping straight to the suitability. I'm not trying to now check number of years or if they have an MSc. I'm just jumping from mapping the grad of Ivy. I'm just pretending like the only feature I have here is the grad of Ivy, and based on the value of the grad, if they're a grad of Ivy League school, if they are suitable or not. So I check if they're a grad of Ivy. So I have some data points. Yes, they are. The suitability is yes. So I have 1 yes, yeah. Yes, they are, and the stability is yes. Another yes, they are, and the stability is yes. So that means that what I have here will be 3. And if we check if there is any yes for grad of Ivy where the suitability is no, the answer is 0 because we don't have any of that. So quickly, can someone do, for when they are not a grad of Ivy, the number of yes for suitability and the number of no. So let's just let's all do it, because that's how, honestly, like, understanding this is the underlying principles behind how decision trees work. So if we can do it, and just put in the comment section maybe 4,1, 2,0, whatever you have counted. And this is a very small data set, so I think 1 minute should be enough for that. So that's right, 0,4. So, okay, so I'm going to explain for the benefit of those that didn't understand. So we'll go back. It's quite straightforward. So I guess I'm not a good teacher as I thought. But let's go over it again. So what I've done here is I've started with my feature of if they are a grad of Ivy. And with the values of grad of Ivy, the unique values, that is, we can only have a yes or no, right? So we have drawn a branch under the grad of Ivy, and the next feature that we are picking is how many of these participants were a grad of Ivy and they were passed on for the interview. So we go through each row because we are dealing with the yes. So we go through each row and we check, okay, these first participants, are they grad of Ivy? No. So we skip that because now we are dealing with the yes. So I'm starting from the yes. And we go to the next row. It's still no. The next row says yes, which is the branch that we are. They are a grad of Ivy. So once they are a grad of Ivy, we then go into this box because the next box for us is to check the if they are suitable or not. So for this particular row, they were a grad of Ivy and they were suitable. So that's one. We go to the next row is a yes and they were suitable. Two yes. We go to the next row, yes, and suitable is also yes. So that's three yes. And of course, this is no, and it does not work with this branch. So in this case, we had three yes, but we never had any of them that were grad of Ivy, which is like they had a yes and the suitability was no. So using that, when we go to the no branch, we start with the first row again. So the grad of Ivy no, which is the branch that we are. And the suitability here is what? Yes. So now is no. So we have one no here. So we have one here. We go to the next one. The grad of Ivy is no, and the suitability is no. So we have our second no. So we have two no's. We come to the third row, but the branch here is no, so we don't have any business. We skip this, we skip this, we skip this. We come again here. Yes, this is no, we are in the no branch. What's the suitability? No again. So we have two here, right? Making three no's. And we come to the last row, where the grad of Ivy is still no, which is where we are. What's the suitability is no. So we have four no's now. And we never had a yes when the grad of Ivy is no. So that's how we came across 04. Awesome. So I'm going to give you, I hope I didn't do, okay. So let me, because I just want to be sure that you understand. Can you let everyone do it, but just hold on. I want to give Dolamu the chance to count, just a minute to count. So let's deal with this branch. So in this case, we are not dealing with grad of Ivy. We are checking if they have an MSc. And I want you to just tell me for this particular node that we have, how many yes and how many no. So everyone can do it, but yeah, Dolamu, yeah, the star boy here. So let's see if you're able. I just want to be sure that you do.
For the yeses, we have like the number of the suitable for yes should be so that should be one.
Okay.
I guess.
So MSc is we are under yes, right?
Yes.
Yeah. So yes. This one, right?
Yes.
Yeah.
Yes.
Yeah, because
and
it's yes. And yes, no.
Yes, no should be, I guess, 3.
Okay. Brilliant. Yeah, you got it. So this is basically, so here we are building, what we are doing is just basically building our parts, our decision tree. So now I've separated it, but the way we saw it in the Titanic dataset, where they started with the gender, and then from the gender, they went to the age, and then from the age, they now went to, how many siblings. That is how a typical decision tree would look like. So it's not like we just go from grad of Ivy and then we just jump to the final output that we are trying to get to. We actually walk through the feature. So a typical part could be, first of all, check the grad of Ivy, and then the branch here doesn't jump to suitability. It jumps to like, okay, their years of experience, and depending on their years of experience, we then check if they have an MSc, and then from there, we walk through the suitability. So this is just a small example of I just want to show two levels of, what a decision tree can be, but it could be many levels, many layers as we walk through each feature. And at the end of the day, we just want to pick the optimal path where we know that every time we walk through that path with an unseen data, it's going to give us the right, it's going to get us to the right prediction, basically. But how do you now draw the optimal path? How do you know which path is optimal? How do you really know that, you know, every time I this particular path in the decision tree is the best way? How do you walk through those trees to find the one that is the optimal? This is where we now have some other things, but I think I've had some questions here. Let's just refresh. Yeah, here I think I just put this to just refresh. So in these two boxes that you have, what are the root node? Remember, the root node is the very first starting, like the very first node that you have started with. The next question I'll ask is, are there decision nodes here? Yes, is a yes or no. So do we have decision nodes here? All right, the answer is no. And okay, the answer is no. I see majority said yes, but the answer is no. We don't have decision trees. I'll go back. So let's go back to decision node. So you know I said decision node are always between, they have something pointing into them and something pointing out of them. Always bear that in mind. Root node is the beginning where we are starting from. Decision node have something and how they have a branch coming into them and out of them. While leaf node just have something coming into them but never out of them. They are like the last. So the one that we have here, the orange, they are the leaf nodes. They have nothing coming out of them. While decision node, something is coming in, something is coming out. So let's have that pictorial thing in mind, and let's go back. So here, let's look at it again. Do we have decision nodes? No. Okay. Yeah, we don't have, because what we have here is just our root node and, you know, the leaf node, because we don't have any other feature between these two nodes. So what's the name of the node between the root and leaf node? I think this one was just to bring confusion, but we really don't have like any node per se, because this is the root node and this is the leaf node. So we don't have any nodes between them, just branches. And now, you know, I mentioned earlier that we have an optimal path. We should have is the leaf node the last? Yes, the leaf node is the last node. So it doesn't have anything coming out of it. It just has a branch coming into it, but not out of it. And the leaf node is actually what we are trying. At the end of the day, the leaf node is what you are trying to predict for your decision tree. So it's the end. So it's saying after walking through this journey of different branches, and working through the data, this unseen data, and asking these questions from the data, this is what I have arrived at. So that's the leaf node. That's the last. That's like the goal where you're going to. So yes, to that question. So I was saying earlier that at the end of the day, when it comes to decision trees, we want to pick the optimal path. And there is something that we call impurities. So impurities is basically the level of the level of purity of your tree, but we'll get to know, you know, what that really means. However, I just want to juggle your brain to ask between the first box, that is the grad of IV, so you can take a guesswork, and the MSc box that you have on the right here. Can you tell me which one looks like a pure tree? I've not mentioned anything about this. I've not told you how to know when it's a pure tree, but I just want you to kind of look at it and think which one is the pure tree. Okay, someone said I think the grad of IV. Any others? None. Okay, someone said none. Okay, let's put it this way. Which do you think is the purest? Which do you think is the purest? Yeah, I don't want none or both. Pick one. Which do you think is the purest out of the two? Grad of IV. Okay, I saw that some people are now changing their mind. All right, awesome. Grad of Ivy. You're right. Yeah. The grad of Ivy is the purest, and we will get to see why. But for those of you that said the grad of Ivy, I guess you probably just checked that which one had zero, right? Most. And of course, the grad of Ivy is the one that has zero most because, and that's why it's the purest because it's so you can imagine like that Titanic data set where the very first root node is the gender, male or female. And once they are female, they survived. So it's the same case where we are saying if they are a grad of Ivy, it's sure. So if you know about, maybe you know about a company and you know about what they are using for their criteria, you can tell someone that is a grad of Ivy, like take it to the bank. You are a grad of Ivy. If you apply to this company, they are going to pick you. That is actually what this tree looks like because every time you're a grad of Ivy, the suitable is always yes in our data points, like across our data set. We never had a case where they were not a grad of Ivy and they didn't pick them. However, if they are not, there's the chance, the probability is very high because zero, like nobody who was not a grad of Ivy was ever selected. So that's the purity of the tree. However, it's not always so in the case. Like you will always have anomalies. Somebody will just come and their profile will just shift the data somehow. So you don't always have this in a typical data set. You don't always get lucky. But the goal of the decision tree at the end of the day is the optimal path works with how much the branches of a particular tree, like the paths, how much it's pure. That is what the decision tree is looking for. How do you measure impurities excuse me? How do you measure impurities in a decision tree, in the path, as you're building the path, building features, asking those if yes question? How do you measure? How do you say this tree is actually not so pure? This is the path that is optimal. This one is more, I don't know if there's an English word like more pure, but pardon me if there is not, but it's just to explain myself. So which one of them has, the highest level of purity, basically? And that is actually how we pick the optimal path. So how do we measure them? Yeah, this is just, I'm trying to explain, this is the green part is the purest. We have many criteria, not many, we have like I think 3 to 4 of them, but in the course of this course we are going to walk through 2 of them, and this is where the math comes in. But as usual, we are going to do the math first before I even show you the formula so that it's not confusing. But yeah, for this course we are going to go through 2 of them. We have the Gini index or Gini impurity. We have the entropy. They both have their pros and cons, and we are going to see when we should pick one over another. But like I mentioned, we have like 3 to 4 of them. We have log loss, I believe, but we are not going to look into all of the criteria. But I can tell you that once you get these 2 criteria, when you come across like the other criteria, they are quite easy to understand once you understand these 2. So that's why I just decided to stick to 2 of them. So now we are going to look at the Gini index and how we calculate it when we are working through our part. So we still have our data set here, and now we are going to start with something different. So this is similar to I don't want you to look at this section. Just ignore that this sections. I probably didn't do my slides very well. This is not supposed to pop up yet, but let's just pretend this is not here and let's work with what is here. So the decision tree will start with, so there is no specifying of, start with this feature when you're building, like your root node should be this feature. So it could be random because at the end of the day, you build different trees. So it's different trees can, as it's building different trees, right? It should be like starting with I have MSC and then going through each of the feature, and then there's another tree is starting with like grad of IV, blah, blah, blah. But we'll still talk about that because that's where boosting algorithms comes in, but you don't have to focus on that. At the end of the day, the feature that I start with could be random. It does not, there's no, okay, is this one you should start with or is this one? But at the end of the day, it is that we explore all of the columns in our parts. So in this case, I've started with like the years of experience. So I've changed things. I'm not using MSc or IB. And this is just to reinforce that we understand it. That's why, so don't be confused. I'm just shifting goals across the features. This is to ensure that you really understand, you know, where we are going to. So in this case, I've picked the number of the years of experience as my leaf node. Remember, leaf node is a starting node. And I've just jumped, I'm not exploring the features. I've just jumped to the suitability. And how we calculate the Gini index is this formula that we have here. So here, what we have done here is to just, so let me just go through, yeah, let's just do it this way. What we have done is I've checked the years of experience by checking less than 3. So the reason why I did this is because in previous slides, the values of our columns have been yes and no. So they are quite easy, right? But what happens when your feature is a continuous value? So decision tree will start, you know, doing things like this. So it can even say when the experience is greater than 18 or 15 or something. So this is the complexity of this. It's trying to find the optimal path. So it's doing many combinations and permutations, if I'll put it that way, and trying to draw the optimal path from this. And how we measure the impurity level is like I mentioned, there are 2 of them that we'll look at: Gini index and the entropy. So we are first looking at the Gini index. So for the Gini index, I don't want to show you the formula, but this is what I've done here is working through that formula in a way that shows you how we use these numbers in those formulas. So just stay with me and I'll be happy to re-explain this part, because once you get this part, it makes other things become easy. So up until this point, so I'm going to draw, please just follow me as I'm drawing my arrow. Up until this point, does everyone agree with the numbers? It's what we have done before, but I want to be sure that you at least understand how we came across, you know, each number. We've done this before, but I just want to check it. Like I mentioned, don't look at this. Don't look at this at all. We'll get there. So let's look at it. So the experience is less than 3. So it picks the years of experience. And like I mentioned, this could be any number. It could be greater than 30. It could be greater than 50. That's how this is. So it does that randomness. But in that randomness is measuring the impurity level of the parts. So, but in this case, let's say our decision tree has started with when the experience is less than 3. And it's a yes and no, of course. Like, okay, when it's less than 3, yes. And then it goes to the next feature, which is suitability. So we are going to count how many years of experience do we have here? Less than 3. Is this less than 3? Yes. So we are still under this branch. The suitability is what? No. So we have 1 here. We go to the next row, less than 3. Of course, no. So we skip that. Less than 3, we skip that. Less than 3, no, because this is 35, right? 1 is less than 3. Yes, it's less than 3. So what's the suitability? Yes. So we had 1 here. 50 is not less than 3. 15 is not less than 3. So that is how we came across 1, 1. All right. So for the no branch, we start again from the very first row of our data point, like our data set. 2 is less than 3. Is 2 less than 3? Sorry, experience less than 3. Now I'm getting myself confused. Experience less than 3. So we are under the no branch. So when we say experience less than 3, that means, you know, 2 is 2 less than 3. So the answer is yes. So in this case, it doesn't fit this branch. So we move on. Is 12, so let me just flip it. Is 12 greater than 3? I think that's just better. Is 12 greater than 3? Yes, so it fits this branch. So what's the suitability? No. So we start counting. We have 1 no. 18, but the yes, the suitability is yes. So we have 1 yes, 1 no so far. We move to 35, which falls under, the suitability is yes. So now I have 2 yes. We move on to 1. 1 is not greater than 3, so we move on. 50 is greater than 3, so we had 1 no here, but now we have another no, 2 no's. 15, which is the last one, is greater than 3. So the suitability is no. So we had 2 no's before, now making 3. So it's basically what we've done in the previous, is it grad of IV and all. Awesome. So everyone is on the same page. Now we walk through the formula. So we start with the 1 here. You've done naive Bayes, so I'm going to assume that probability is not an issue. But please feel free to call me back if you find the next part I'm about to explain, difficult. So what we want to do is to check the probability of when the suitable is yes, like we are working with the leaf node, like, because that's what we are trying to do. We are trying to get to the leaf node and calculating from the leaf node. So we get, for yes and no, and then we raise it to the power of like 2, like raised to power 2. We'll see the formula, so we'll now relate the formula back, but I felt like it's better to just walk through the math first before we go to the formula. So we start with the, ignore this part because it's part of this 1 minus is a constant that's part of the formula, which we will see later on. But this 1 minus has not come from anywhere in our data point, it's just a constant. Now, we want to sum the probabilities of it being a yes or a no under this particular part that we have walked through. So we start with the yes, where we have 1, and of course we know probability is like the probability of yes is like, let's say flipping a coin is 1/2, like head or tail, right? So 0.5, 50% chance. So we check for yes. We have 1 yes here. How many do we have in total under when this experience, like under this branch that we have come from? We have 2. So it's more like saying this one plus this one, the sum of it. But now we are doing the probability. So that's 1/2 raised to power 2. The raised to power 2 is also a constant in the formula. And then we add it to the probability for no, which is like 1 over the total sum, 1/2 raised to power 2. And of course, I believe my math is correct. The final thing that we have here when we do this, and thank you, Fortune, because I made a mistake with how I did my brackets before, but he went through my slides and was able to like put some corrections. So thank you for that correction. So at the end of the day, what we have here is 0.5, and 1 minus 0.5 is 0.5. Moving on to this case, we are repeating the same thing we've done here. What is the total that we have? We have 5, right? What's the probability of the yes? Is 2/5 raised to power 2, plus the probability of no is 3/5 raised to power 2. And everything here becomes 1 minus 0.5. Excuse me, 1 minus 0.52, which is 0.48. So when we've done this for that particular part, we've calculated the probabilities with this formula that we're going to see. We then do what we call like the weighted Gini index, because that's actually what we want to do at the end of the day. So the weighted Gini index is now working through the whole branch, let's just put it that way, the whole data points, basically. And we will move to this, the weighted one comes from here, where we now check under when the experience is less than 3, how many suitability did you have? So we are not checking if it's yes or no in this case. We are just adding how many suitability did you have when the experience is less than 3. So we have 2, right? Because we have 1 here, we have here 2. So basically what we have here that we are the denominator, numerator. I think it's numerator. The numerator we have here anyway is what we bring here divided by the total number of data points we have. So we have 1, 2, 3, 4, 5, 6, 7. And in fact, by the time you add whatever your leaf nodes, by the time you add these values here, they should give you 7. So 3 plus 2, 5, 6, 7. So we start with the yes branch and we say how many suitability? 2 over the number of the samples of our data times that probability that falls under the branch. So that's what we've done here. Given this, can anyone, I want to, the next thing just to gauge that, you know, you understand what we've done here is to ask you to tell me what the value of, you know, just put it in the comment section. For the no, when the experience is less than no, we want to calculate the weighted Gini index. So I'll give you a minute to figure that out. Awesome. Scholars. Let me be hyping you people. So what we've done is, I believe you've understood up until this point, right? So the weighted Gini index moves to the next level of, you know, when the experience is less than 3, how many suitability we had under that. So we had 2 suitability because one is under yes, one is under no. So basically we have 1 plus 1, which is 2 over the total number of the data set we have. So here we have 1 row, 2nd row, 3rd row, 4th, 5, 6, 7. 2 over 7 times the probability that we've calculated for, you know, when it is yes and no. That's what we have here. And how we came about 5 over 7 is that we added this as well. The same we added 1 plus 1. How many suitability under no when the experience is less than 3 is 5 over the total, which is 7 times the probabilities, basically. That's how we arrived at 5 over 7 times 0.5. And then when we, you know, do all of this and then add it to the summation, basically, of this, it gives us 0.48. So what we've done here, this is the formula. That's so I don't know, I can't remember who asked, but someone was asking, you know, if it's a formula. So this is actually the formula. So if we trace it back, we have 1 minus, so the Gini index now, 1 minus the summation of the probabilities for each instance. And of course, we have the raised to power 2 here. So that is basically what we've done here. Okay, I'll be moving a bit faster now because of time. But the best case scenario is when your Gini index is 0. If we look at, I want to go back to this. If we look at this, you will see why we say this one is pure. Because by the time we do the Gini index of this, when you are doing 0 over something, it's going to give you 0, right? Like, do you get what I mean? Like if you're doing 0 over 3, it's going to give you 0. If you come here to as well and you want to do for this, you know, yes, it's doing 0. So at the end of the day, when you actually calculate the Gini index for this particular you know, branch or part that we say is pure, you will see that it's going to give you 0. So this is where the purity comes in. So the lesser your Gini index is, the better. So once it's doing all those branches and it's calculating those weighted Gini index across each part, it's just going to keep going for the one that are the values are close to 0. That is actually the criterion for these parts, like in this particular, you know, for when we are using Gini index. When we walk through the parts, the closer it is to 0. Looks like we are doing chemistry. Oh my God. The closer it is to 0, the better for the parts for us. Like it just means that that part is optimal. Hopefully I'm not confused people. Are we trying to consider the number? Someone asked, are we trying to consider the number of children in each branch so we don't have problem of imbalanceness? So maybe if we have the same children, then we don't need to weight them. Yes, it's part of the parameter. So when you go to like sklearn, like you can determine like the number of children that you want a particular Someone is saying ML and maths. Oh God. Anyway, you want to that you can restrict the number of children that you have. So at the end of the day, you can decide, okay, I don't want this particular branch. I don't want it to have more than a particular number of splits. So at the end of, there are also, we'll get to that part of, balance and imbalanced data sets. So, but at the end of the day, when you have, it's not really about the number of children, because if you say the number of children under this branch, number of children under this branch, they will not be under the same conditions depending on the data points that they are using to work through the number of children. So yes, we consider that because the number of children determines how deep how deep and wild your decision tree will grow. But at the end of the day, that's part of the algorithm figures that out when you give it those conditions. So I hope I was able to answer. It was just a private question that I got from Peju. So I hope I was able to answer that. Someone said ML and maths, but this is not hard now. Not hard. So let's go to the entropy. So in fact, I feel like this one, I didn't do this slide very well. Oh God, help me, Lord. Okay, let's go through this Gini index again. So remember, like this is the Gini index, right? And we do it per node, but at the end of the day, we still have to do the weighted Gini index. Now for the entropy, is almost the same formula. I just want you to look at this and look at this. The difference that you see here is that there is no 1 minus. In this case, we are multiplying the probability by the log of the probability. So I just want to go back to show us something. So I don't even know why I've used this particular. So in that other formula where you have, you have what we have here, just this section of the Gini index minus the probability times the log of the probability. So looking at, I've used this particular scenario for the example of the entropy formula that I used. So, but looking at this, it means that we'll have, log of 2/5 times the log of, 2/5 plus the plus 3/5 times log of 3/5, which is like what we have here. So the entropy is, is like I said, if you understand this one, it makes this one easier because you're just doing the summation of, the probability times the log of the probability. And we've done that so you do it for each instance, like this, yes, and suitability, no. So this section shows the yes side, while this section shows the no side. And it's the same thing, like when it is closer to 0, you pick that particular branch. So that's just that's entropy basically. That's how it's different from the Gini index. And how do you know which one to really use? There's no fast route to like every time use Gini. On sklearn, actually the default criterion is Gini if you don't select anyone, but they have like log loss, they have the entropy. So the entropy, you can select the criterion that you want on sklearn. But something to bear in mind is, understanding your data. So this is where data analysis would come in, where you're trying to analyze if you have balanced or imbalance, like, someone raised the question about balance or imbalance. So the Gini index is less sensitive when you have class imbalance. So class imbalance is, this one is quite balanced because you have, yes, sorry, I didn't mention that you also weight the same way with, done the weighted Gini index here. You also weight the entropy. The difference is just that the formula here is different from the entropy one. So yeah, you do the weighted entropy as well. The only difference is, this formula at that node level. Okay, I was saying, Gini index is less sensitive to class imbalance. So this particular data set, I think is balanced. You can say it's balanced because out of 7, at least 3 is yes and 4 is no. If it's like maybe 1 is no and 6 is yes, then or 2 to 4, you can say that's not a balanced data set. So Gini index does not really capture when you have imbalanced data. But entropy is very good with that. And when you have an imbalanced data, entropy has a way to seek more balanced splits because of the logarithm that is introduced into its formula. And of course, in maths, when we are doing logarithm, it's computationally expensive. So if you are doing 2 plus 2, it's very easy. If you are doing log of 2 plus 2, the logarithm is takes the computation a bit higher. So when you are training your model, if you are using Gini index, you know that you are able to train faster because Gini index is just summations of and additions. But with the introduction of log in entropy, it means that is there a reason why you did not account for the negative in the formula? You mean this particular negative that we have here? I guess that's what the person. No, there's no reason. This is, you can honestly, I'm not a math guru, but you can just ignore you can just ignore this part. It's only when when you have like let's say what you have here now is minus 0.48. So it means that if I'm doing 0.5, right? Like if I'm adding something positive to negative, it will be something positive to negative, it will be negative. So that's why you have that negative there. I think that does look at it from that angle. I hope that makes sense. Is the 3/5 for illustrative purpose? From the example, this P underscore I is equals to 1/2. So let me go back. It's not 1/2. This one is for this example when the experience is less than 3, while this one is when the experience is greater than 3. So the example, the illustrative thing that I've put here is for this other example here. It's for this particular, when it's greater than 3. So that's what I've done here. Yeah, I calculated it for the second one. Sorry if that was not straightforward. I'm really sorry if that was confusing. I didn't calculate it for this one. Yeah, that's something I should have bear in mind. Yeah, I calculated it for when the experience is greater than 3. Okay, I think I see, I think maybe that's fortune. The logarithm of probability values, which are typically between 0 and 1 is, I didn't even factor this in. So the minus outside makes it positive. Let me think about that. The logarithm of probability values, which are typically between 0 and 1 is negative. Oh, I see what you mean. So the minus will always make it positive. That's what you say. So do you have a case where, the logarithm becomes negative? No, I guess you're saying, it becomes positive rather, like the logarithm is a positive number. I guess you should have cases like that, or no? Log 1 is equals to 0. So when log 1 is equals to 0 and this is negative, that will be negative and not positive. Or when it's less than 1 is negative. Okay, so that makes it positive. But when it's like log of 1, for instance, it's positive and this will still be negative. I don't want to confuse people, but I think that's, depending on whatever value you get here anyway, if it's plus or if it's minus, if you do minus times minus is positive, but if it is plus and you do plus times minus, it still becomes negative. I hope that's clear. All right. So, depending on whatever you have here, your plus times minus, it's always negative. I'm going to move on fast. Okay, I think I've explained, the difference between when she was in. All right. So, something that I mentioned at the early stage of when we started this course is that, decision tree recursively does these iterations, and it its goal is to find an optimal path using either Gini Index or entropy or some other criteria. And so when we are doing like that recursive partitioning, there are different, hyperparameters tuning. I didn't cover all of them because there are many of them. If you check, when I was checking sklearn like some days ago, just going over the parameters, I think I saw like 10 to 12 parameters. But the good thing is that when you go to sklearn, it's explain what each parameter does. But I think I selected about about 3 of them. So one of the criteria that you use, because you are doing a recursive action, right? So recursive is there's never an ending to it. Like when you have a for loop that is not ending, or a while loop that is not ending. And there are some things that you can use to stop the growth of the tree. And one of them is the max depth, which is a parameter you can set when you're building your model. You can set the maximum depth or height of your tree, like how deep you want it to go. Like in that Titanic one, you can see it has like three layers, or is it 4 layers? I can't remember. Like it had like 3 to 4 layers. So you can decide to say, as I'm building this tree, once you reach the 5th level of a particular branch, just stop the tree there and calculate the Gini index and give me the best. So that's one way to stop it from just growing excessively. You can set the maximum depth or height of the tree. The minimum samples per split. You can also define the minimum number of samples that you require in a particular, at the leaf node, like how many samples do you want, how many features do you want to go through before you get to the leaf node. So like the ones that we had, I think it's just one sample. I went straight from experience to the suitability. And someone is unmuted. And then another way you can stop your tree from that recursiveness is also using early stopping. So you can have, I believe cross-validation is not something that is new, but cross-validation basically is to monitor the performance of your tree on a validation set. So on a set that was not used in the training. So you can say, when the validation score is like up to this particular value, then you can stop growing the tree and just pick the optimal tree for me. Model interpretation. So I would explain, like, maybe we may have heard about AI explainability or interpretability. So a use case scenario where interpretability is useful is in healthcare, for instance. So one typical model that you build for a healthcare system is probably a deep learning model that can classify if a scan, if a particularly a brain scan is cancerous or not, for instance. And interpretability helps us to understand how the model has made its decision. So maybe you pass in an image and it says it's cancerous. It wants to know, like, how did you arrive at this conclusion that this particular scan is cancerous? So in healthcare, for instance, interpretability is widely used because they want to be able to what's the word now? They want to be able to understand why the model has made its decision. So people, they are like a whole box of research going on, like to interpret models, because most time they are seen as a black box. You can't really unravel why they have made that decision, but there's a whole research that is dedicated to like interpreting the model, understanding why it has made the decision. So there are deep learning models that are being built in the healthcare system, where it's not just predicting that, oh, this scan is cancerous or not, but it is also, explaining, showing visual explanations for some cases, while like BradCam is one algorithm that is used. Why it has arrived at a decision, like highlighting maybe some portions of the image that shows that this is why I've said it is cancerous, or highlighting some parts of the image to say this is why I say it is not cancerous. So this is what, interpretability, I think some people say there's a difference between interpretability or explainability, but I've tried to research both terms, and for me, I feel like everybody's still just doing the same thing. It's just nomenclature. So for some models like naive Bayes, SVM, linear regression, and all that, because they are a mathematical model where you are saying, attaching, this formula with this set of input features, give me this output variable. Because you are establishing a mathematical equation between the inputs and the outputs, they are quite easy to interpret, because we know that a lot of maths is about proving theorems and proving formulas and all of those things. So you can easily like prove it with maths, but because decision tree is not a mathematical model, the turn of interpretability it goes away from like the mathematical modeling to now looking at some other factors like the decision part. So I'm going to show us later later on how a decision a decision part looks like, from a decision tree. But basically, one way we can interpret it is by extracting the rules from the part, the optimal, that it has created, maybe the optimal part, or the part basically. And converting that tree structure into a set of if rules, like we've seen earlier, like if rules. So that thought that you had about, is it if else? Yes, we can say it is if else, but it's not just a random if else. There are criteria that we are using to measure how we go through that if else structure. So that is one way to interpret decision tree. There's also feature importance. So a good example of feature importance is that Titanic data set, you see that from the very beginning, when the gender is female, it just went straight to the fact that they survived. We are not even checking any other information, if they are age or siblings or whatever. It's like when they are female, they are more likely to survive. And I think there's something about it in the fact that they said when the rescue boat came, the women, of course, the men are good men, so the children and women are actually the people that survived most in Titanic. So when the rescue boats came, people that were children and women were the first to go until everything just collapsed and all that. So in that case, we can say a feature that they prioritize children. Thank you, Teju. So we can say that when we are drawing a feature importance from decision tree, for instance, we can say if key feature that we cannot even remove is the gender and the age. So in this case, if you are a woman, like if person is a girl, and a girl, like, so when I say a girl, of course, maybe around age of 13 to 15, we can say they survive. So feature importance is a way that you also measure, you interpret your decision trees, because when you're looking at the trees, like we saw in the Titanic data set, we can easily say this particular feature is very important. We can't remove it from our tree because it's important for us to know if they survived or not. Whereas some features like maybe I don't know which feature I can say, maybe where they embarked. Of course, some people even say where they embarked was important because I don't know, or probably the cabin, the cabin where they are. Maybe when the boat turned, for instance, the people that are the other side of the cabin, they were still surviving there, but some other people that were there when the side that turned to the water, they didn't survive. So cabin position could be an important feature, but probably where they join, the port at which they join the ship may not be an important the class. Yeah, exactly. First, I don't know. I didn't watch the movie, so I don't even know if the class is an important features. So, money is good. I did not know. Money is good. Have money in your life. I actually didn't know because I didn't watch the movie. So you can see like the class that the people are important. So this is where interpretability comes in when you look at the tree, because you can walk through the part of the tree and be like, okay, this based on the optimal path, these features, that falls into those optimal paths, they are actually important to us. While some other features, because they didn't show up in the optimal path, they were not really useful for us to know, what the output would be. And then visualizing DT, which is what I mentioned. There's a way you can visualize, the if then else, like visualizing is what we have seen so far. Basically, like looking at the tree and the branches and how they go. There's a way you can actually build your decision tree, and after that, look at all the parts and then looking at the optimal path as well. So that is how you actually. It's not something that we can really have some proof of theorem or something in terms of like maths. We have to actually do more of like manual work of checking the parts, looking at the feature importance, and things like that. And then when do you use decision trees? When you don't want to do data cleaning, so maybe you have a very messy data and you need to deliver a model fast and there's really not much time to do data cleaning. Decision tree is it works well with unclean data, like it works well with messy data, because no matter the data points you are giving it's not trying to do a mathematical formula, or it's just building trees and using some criteria to choose the optimal paths in that way. And of course, there's no need for outlier treatment, like that example that someone said, or even when you had experience greater than 50. Of course, if you are not from high school and you have 50 years of experience in that particular, and your experience is related to the role, there's no reason why you should not be selected. So you have what we call like the anomaly or like outliers in your data, where those people, the features that they have and the outcome is not looking like the rest of the other data points. And when you have missing values as well, decision trees are perfect. Or when you don't want to go into a lot of trying to understand which feature is important, is you figure it out by itself using the optimal path. When not to use decision trees is when you have like high variance. So what do we mean by high variance? When you have a tree-based model, we say a tree-based model is very complex, and when we say it's complex, it means that it captures a lot of noise or random fluctuations in the training data, rather than focusing on like underlying patterns or relationships between the features. So that's what we call like high variance. It would, in that kind of instance, it would actually work well with your training data, but it would not work well with an unseen data. And if you have heard of overfitting, this is like, high variance is often associated with overfitting. So it has overfitted the training data such that it can't, like when you give it a new unseen data, it just fails woefully. The accuracy is not, and one way to measure it is like using cross validation. You would know from your cross validation that your data, your model is not doing well. So when you have very high complex data, high dimensional data, for instance, this is where you should not use decision trees. Although maybe I will not say not, because there are ways to actually overcome this problem in decision trees. So a high dimensional data could be a tabular data that has like 500 columns, for instance, like 500 features, but in terms of the data points, like rows, now you now have like 200. Like that's high dimensional, and in that case, decision trees may not, because decision trees really thrive when you have a lot of data points rather than a lot of columns, if I can put it that way. So that's not, if you have those kind of data, decision tree may not be the first model that you want to use. You may probably just want to go for other models, like your mathematical models that you've done in the past, I believe. But there are also ways to like combat this. This can be solved, and we'll see that in the next slide. So pruning is what we do in decision trees. And it's basically a technique that is used to prevent, overfitting in your decision trees. So as I mentioned earlier, when overfitting occurs when the tree is just so complex because it's high dimensional and it captures too much noise and can only fit the training data. It can't work on unseen data. You can actually do what we call pruning by removing subtrees that do not significantly improve your predictive accuracy. So of course your accuracy is made. So for a classification model, the accuracy, you can use different metrics like accuracy, precision, F1 score, and all of that. So from there, you can decide to remove trees that are not improving your model. So pruning is one way to avoid that high variance. Okay. So let's go on. So boosting methods. So just by the word boosting method is, we call it an ensemble. We have different assembling technique like random. I don't know if you guys have done random forest or would do random forest, but random forest is also an ensemble method, but it uses the bagging method. But the boosting method is another type of ensemble technique. And like the word ensemble is like, trying to improve something. And it combines the predictions of multiple weak learners. So if you are using a boosting algorithm with decision trees, it means you have many decision trees, like you have many trees, and you are using you are trying to boost those decision trees by leveraging their weaknesses. How do you know their weaknesses? When the places where they have misclassified, that's what we refer to as, their weaknesses. So you are trying to improve why they have misclassified a particular unseen data. And this is where boosting algorithms, so they are different. I don't know if they are different to algorithms. They are different, many boosting algorithms, but there are two of them that are highly popular, and those are the ones I'll just explain how they work in this scenario. So what it does is, looks at these decision trees, look at the scenarios where they have misclassified, a particular boosted. The difference is that they are both ensemble methods, but the random forest uses the bagging method. The bagging method is different from there are differences between the bagging method and the boosting method, but they are trying to achieve the same thing, like that is work on the weaknesses of the decision trees, but they have different approach. I think for the bagging method, it does it in a parallel way. That's one of the difference between the bagging method, which is where random forest falls under. It does the learning, like the improvements in a sequence, in a parallel, like everything is like being done at the same time. But for a boosting method, the boosting method will start from a particular decision tree, look at why it's failing, like on some scenarios, improves it, and then what it has improved in, like let's say you have 5 decision trees, for instance, what it has improved in decision tree A, like, or 1, it takes that to decision tree 2, and then what it has learned from why decision 2 is failing, it takes, from 2 and takes it to the 3rd one. So it's done in a sequence. That boosting is done in a sequential order. But for bagging, it just does it at the same time and then does like an average selection over the trees. So that's like they have many differences, but that's one difference between bagging and boosting. So I hope that makes sense. So there are two major, I don't know if there are new ones. Like I said, like this is, so forgive me, I said it earlier, like disclaimer, this is not my regular day-to-day things that I interact with. So I don't even know if there are more boosting algorithms. If there are and you know them, please feel free to mention in the chat section. But for the purpose of this course, I've only listed 2 of them. And they work differently. XGBoost, which basically stands from extreme gradients. The way it works is that it focuses its attention on pushing, the limits of, of the accuracy and speed. So it uses techniques like regularization techniques, like we have like L1 regularization, L2. I don't want to dive deep into how these regularization methods work, but we have like L1 regularization, L2 regularization, tree pruning. So it does different different, its approach to boosting is different from like LightGBM, and it has like a parallel processing at the same time. So although I've mentioned that for boosting we do it in a sequential order, but when it comes to like XG boosting, because of how the algorithm has been built, there's a way it can do it in parallel and still communicate the information to, as it goes on each different decision trees. Hopefully that makes sense. So that's the algorithm has been built to still do it in a parallel way, even though we want it to, and still pass the information from one tree to the other, like learn from your senior. This is the mistakes it has done. I want to correct you so that you don't make that mistake. So it still does it in a parallel, processing way, but I still want you to have it at the back of your mind that boosting is done sequentially and not like parallel. And then LightGBM, GBM here just stands for gradient boosting method. It uses an histogram-based learning, which is different from XGBoost. So what it does is that it groups data points with similar features. So you can look at it like by rows. It does like a count of, okay, row 2, row 5, row 7 of my data sets, they have similar attributes in terms of the values of their columns, like they have many similarities. So I'm just going to group those ones and use that to train, the decision trees that I've misclassified. So it tries to like understand, groups. That's why it's called a histogram based, because it groups things together according to the features that they have in the samples, and it uses that to correct the weak learners, which are the decision trees, basically. So they are both boosting algorithms. What they do is to correct mistakes from trees, but they work differently. And I'm also highlighting like some strategies that they use. So for XGBoost, it uses a depth first search. So I want to assume that depth first search is not something that is strange, but depth first search just goes from top to bottom of the tree without expanding every other branches. So if it starts from a particular node and it goes to the next node, like is the age greater than 10 or something, it just keeps going down that branch, and then before it comes to the top again, goes down. So it uses a depth first search approach, whilst LightGBM, it grows it by expanding the part that reduces the loss the most. So basically, when you are training, you're also doing cross validation. So as it's building the parts, if there is any part that is looking like it's just the loss there is high, like it just ignores it and continues with the parts that the loss is low. When you check, the accuracy or whatever metric evaluation you are using to evaluate your model. So that's how it works. So they have differences, but it's the same goal that they are trying to achieve. When it comes to handling missing value, so why I'm going through the differences is because it's good to understand your data. Understanding your data is key. Doing statistical analysis is key to knowing when to use decision trees for a start, and when to know which particular if you want to use a boosting algorithm to increase the accuracy of your decision trees, which one should you go for? They all have pros and cons. So XGBoost, for instance, uses a sparsity aware algorithm, and what that means is essentially an example of a sparsity aware algorithm is that it avoids creating branches or nodes that have features with null values. So in this case, like when it's trying to correct decision tree, it's not going to, if it says that decision tree, for instance, because we mentioned that when to use decision trees when you have missing values. So because of those missing values, sometimes decision trees can, start malfunctioning. So this is what boosting algorithm does. So in that instance, it can just start, if it's using a sparse aware algorithm to correct, the particular tree, that means it's going to remove trees that have missing values. So it's going to optimize the tree structure such that if there's any data point that have missing values, it just prunes, that branch away from the tree. And then for LightGBM, the algorithm has been built to just, by itself, efficiently, during the training process, handle missing values. To be honest, I've not gone into details to how it does that. But unlike XGBoost, where you have to attach it to a particular sparse aware algorithm, the way they've written LightGBM, it just handles missing values automatically. Memory usage. So if you have a computer and a training, maybe the specs are not that high, XGBoost is a choice because it's not a choice, sorry. It consumes more memory compared to like LightGBM, where LightGBM has been built to, manage memory basically. So depending on the hardware you're using to train, and you have maybe a large chunk of data sets, you want to consider your hardware before you know which one to pick. And then lastly, as the data set grows in XGBoost, it becomes slower, especially when you have increased number of samples, it will become slower, but LightGBM has been literally built to handle large data set efficiently and usually is faster than XGBoost. So those are like the major differences between these two algorithms. So if you go to using the link, this link is already in the slide. If you go to decision tree, so this is the classifier method. There is also the decision tree regressor, but this is the classifier method, which is, for binary classification or multi-classification. I just remember that I wanted to show us what visualizing the decision tree looks like. So this is an example. Let me see if I can zoom. Control plus. This is really but this is an example of what visualizing a decision tree looks like. So you can see how this one is even small. Some are larger than this because the decision tree really depends on the number of observations, like the number of data points or rows, so if I say data points, observations, and samples, it just means the number of rows for your data set. So this is just what visualizing it looks like. And if you check the reference section in the slide, I have put like the code for this. I have actually put it there. The link, the article that actually shows the code is actually very simple. It's also on sklearn. So if you are building your own decision tree, look at, if you want to build your own decision tree, I will highly recommend you look at the references because I've put articles there that can help you do that. But it's just anyone can go to sklearn and just copy the code and say they know about decision tree. But the difference is that you understand the nitty-gritty of what is going on behind the scene. So that's why I covered that part most, because I feel like there are many ways. If you want to just learn the code part, that one is easily accessible. But this is sklearn documentation, and you will see that, here, like I said, it has many parameters, but I only explained, I think, 3 of them. So the criterion, so as I said, the default is Gini, but they have entropy, they have log loss, and they are quite, if you read it, you see that it's the function to measure the quality of the state. So how pure or impure they are. So the quality of the split, and using that to draw out the optimal part in our tree. And also the splitter, we can decide to choose the split at the strategy to choose the split. So we can decide to say go for the best split based on the criteria, for instance, or just do random splits at each node. The maximum depth, as I mentioned, how deep you want your decision tree to go. You can, the default is none, so it just means that in this case, the recursiveness would be based on something else, not the maximum number of depths. So, but you can decide to put how many, the maximum number of depths that you want to go, and it will terminate once it gets to that number. But if you leave it at none, then it means that it will keep doing it until it's able to find, the optimal path. Or it uses, some other criteria, like the minimum sample split is another criteria. So this one just means, the number of samples that you want to split at each internal node. So remember that the internal node is the decision node. Decision node is when you have a branch coming into the node and coming out of the node. So you can set the number of sample splits you want at that particular node. And there are many more, parameters that you can set in your decision trees, but I think I'll stop here. And as I mentioned, please look at the references. It's very good. Like, it's really, especially these last two. They have a tutorial on, but let me just show you guys that one, because I think they did a brilliant job to go through decision tree, and they even, like, they explained some other concepts that I haven't explained, because we can't cover everything. And then they went into the code, and I even like that they put OpenAI, because you can literally say, explain each line of this code for me in a way that, it just explains. So please check out that datacamp.com. It's also there that they show us how you can build, how you can visualize your decision tree to see how it's making its decision. So do check that out. It's in the slides. I hope this has been useful. I hope so. I don't know if there are more questions, but thank you. Thank you for staying true, for those that stay true. Yeah, and I'll stop here.